Okay, so I'll go ahead and get started for today. So as you probably saw on the Canvas announcement, the topic for the quiz 3 will be on oscillations. I'm giving you the big hint that that will include solving for the time when some position occurs. I tried to make the problem kind of fun, but we'll see how that goes. But it is related to a biological oscillator. So hopefully that's at least within the realm of interests that a lot of people have here. So we'll hop back into the last bit of chapter 15 on oscillators and then move on to chapter 16 today, which is on traveling waves and some of the phenomena associated with them, most importantly, the Doppler effect. So anyways, the last thing we were discussing in chapter 15 is this idea of a driven oscillator, where either you have something that's, like a pendulum swinging back and forth, which is, for example, a child on a swing, or, you could have a mass on the end of a spring, or really anything that's connected by some, bond that's rigid in both directions. If you look at small enough movements, then that will be well modeled by a simple harmonic oscillator. And so in any of these cases, if you try to give energy to the system, you have to do so in a way that is also periodic, right? If I have someone swinging and I give them energy by just pushing my arms out and then leaving them there, they're not going to have a very pleasant time. And then, like we discussed with this picture on the left, which is known as a response curve, the x-axis is the frequency that we're adding energy with, and the y-axis is how that affects the amplitude. So how strong we say the response is. So if you're thinking about this in the context of a child on a swing, which is just a driven pendulum, then the pendulum has some natural frequency that it likes to swing at if you weren't pushing. That's just, based on omega being root g over L. And if you give the pendulum energy at that frequency, then you will naturally cause the amplitude, the height of the swings to increase and increase and increase. And the little kid will be super happy. But if you try to give that child energy at a lower frequency, that would be pushing, more slowly, fewer times per second, then it's not going to work very well, because sometimes they'll be swinging back towards you while you're trying to push them, right? And very similarly, if you try to give them energy at a higher frequency, so on the right side of that plot, then again, oftentimes when you're pushing them really fast, you'll be pushing against them when they're trying to swing back into you. So it'll end up not being very productive. You can see that the response to that sort of driving frequency is very small, meaning that you're not going to actually cause them to swing by pushing them that way. And then there's an important detail in this plot on the right, which you don't need to know how to talk about quantitatively for this class, but I do want you to have a qualitative understanding of this, which is that so these B values, remember, this is related to the friction in the system. We said that there's some drag force that goes like B times the velocity. So the more B that we have, the more friction in the system. And what you can notice is all three of these curves on the right have the same natural frequency, which seems to be about 2 hertz. So all of them, if you push them at 2 hertz, that's how you get the child, for example, to swing higher and higher. But they have varying amounts of friction. So the one that's purple has very, very little friction. So that would be like a child swinging with a very well-oiled, chain and axle and everything. And you can see that if you push that child right on their natural frequency, that they're going to have a huge response. Every time you give them energy, it's going to go into their swinging motion, and they're going to just swing higher and higher and higher. However, if you have a system with more friction, so let's say it's a old swing set at some rundown playground, it's a little rusty, definitely hasn't been oiled well or maintained. Maybe that's more like this blue curve. And there are two things I want you to see here. So one thing is the obvious thing, that if you push them, even if you push them at the perfect frequency, they're not going to swing as high as the kid on the well-maintained oiled swing would. So that's one important but probably obvious observation. But the other thing is that the width of that curve, it's bigger. So it's a wider response, we say. So the more friction there is, the less sensitive the system is to having to be pushed at exactly its resonant frequency. Okay, sometimes we call the natural frequency a resonant frequency in the context of driving oscillations. So if I'm pushing the kid on the well-maintained, really, beautifully oiled swing, I have to really be pushing them at exactly the right pace, or I'm not going to be able to get them to swing higher and higher. But on the crappier swing, that's less well-maintained, has more friction, I can push them, a little bit too fast or a little bit too slow, and those are okay. The kid's going to basically have a very similar experience of having energy transmitted to them, even if I'm not exactly matching that natural frequency. And then in the most extreme case here, you can see that for this green curve where there's a lot of friction, that there's not a huge benefit to pushing at the right frequency, but that effectively I could push it, anything close to 2 hertz, and I'll be able to give them a similar amount of energy to what they would have transmitted if they were being pushed at exactly 2 hertz, that resonant frequency. So the thing I want you to know is that the more friction there is in the system, the smaller the response we get, but also the wider the region of frequencies we're able to push at where we do get a response. And so if you want to read more about this, it's quantified with what's known as a quality factor, often written as the letter Q. And this is something that engineers are really obsessed over in a lot of large-scale building situations, because the quality of a building really determines what will happen when the wind blows on it, for example. So you want some sort of balance, because if it has no friction, then you're going to get really high response. So when the wind happens to blow at that perfect frequency, your building's going to shake like crazy and fall down. Whereas if you have a system that has a lot of friction, but maybe not enough to just completely quiet these driving forces, then it's similarly a bit dangerous, because you don't have to hit exactly that resonant frequency. You can hit somewhere in this range and still have negative effects. And so one of the most dramatic examples of this is this real phenomenon where some like opera singers or just strong vocalists are able to shatter certain types of glasses with their voice. And we're going to try to get a demo of this. The physics department can hook us up, but it's one of the hardest demos to do, because they're basically, in order for this to happen, we have to have a system with very little friction, which means you have to get special kinds of glasses, typically really expensive ones, so sort of quartz crystal or old leaded glass goblets. And additionally, because there's such little friction in the system, if we draw the response curve, so frequency versus response, it basically just looks like a line. So if we hit even a little bit off from that resonant frequency, nothing will happen. It'll be really boring. But if we can hit exactly at that resonant frequency, we'll transmit so much energy to the glass that it'll be unable to handle it and shatter. So it's a really cool effect. And actually, if you have a strobe light, so something flashing black and white really quickly, you'll be able to see that the mouth of the glass will like stretch in a very plastic way that really is surprising, considering we usually don't think of glass as being able to stretch that way. But it's because in these sorts of situations, you're really pushing that material to its structural limits and actually past them, because we see it break. And then in biology, the book in section 15.7 has a really great discussion of how resonant frequencies and these sorts of driving forces are what allow the ear to distinguish between different frequencies. So effectively, different parts of the cochlea, which in reality is curled up on itself, but we can just uncurl it, which is the picture on the right, and look at it this way. So different parts of it have different resonant frequencies. So if we think of them as a spring, they have different root K over M's. And so when we start speaking, or if some noise is being made where the sound waves are incident on the cochlea, then we'll get different parts of it resonating for different frequencies. And due to some electronic sensors, basically, within that structure, we're able to tell which part is resonating and distinguish the different frequencies. And so that's why you can hear me right now, is because of this resonant frequency response curve. And you can see that each little section of the cochlea has its own response curve that's sensitive to a different frequency. So a cool example of this in biology. And then just for your own edification, if you go back to look at these slides, there's a section at the end of each chapter that's like a summary section. I would really encourage you, if you're trying to gauge your understanding of that chapter, it's a great place to look. But if you don't want to flip back there, I decided to add these to the back of the slides, just so you have somewhere where all the formulas are kind of consolidated. Okay, so before I move on, are there any questions about oscillations? Otherwise, we'll move on to traveling waves. Yes?
It's kind of like 2 days ago, but when you're looking for the phase, is there any way to know if it's going left or right without looking at the picture? Like, you just plug it into the velocity equation?
So you're saying if I give you a phase and you want to know if it starts off moving left or right?
I think to find the phase.
So if you have to find the phase, we actually have to tell you initially whether it's moving left or right, because otherwise there's a duplicity. There would be two possible answers, because there would be one phase where you were at that position initially moving right, and another phase where you're at that position initially moving left. So we have to tell you which, some extra bit of information so you can know which is which.
Okay, so if it's moving left, then you can assume that it shifted left. If it's moving right, you can assume it shifted right.
So you have to be a little bit careful with that. But if you're thinking about like a cosine, for example, then if we imagine, so looking at this blue cosine curve right here, if we imagine shifting it right, then we're going to get something like this, which is a negative phase, right? In order to shift a function right, we have to subtract. And so that would be initially moving to the right, has a positive slope. Whereas if we shifted it to the left, which would be a positive phase, then we have initially moving in the negative direction. So looking at the graph can be really, really helpful in these situations. You just have to remember these function translation rules, that when you subtract something in the argument of a function, that's shifting the function to the right, which feels a little backwards, but it's because when you do that, you can plug in a bigger value for your independent variable, and that subtraction kind of makes it smaller again, which is like sampling the function at an earlier time. So that's equivalent to shifting to the right. Yeah, so I know it can be tricky to hold it all in your head, but it's definitely worth it. Phase won't be too important for the quiz, I'll tell you that. You'll still want to think a little bit about it, but the quiz is mostly going to be about finding the time some value occurs, and then some rather annoying unit conversions, but that's only for the last problem last part out of 4.
And with that time, we know when we find like T1 and T2, we have to plug into the velocity to see which one's going right, which one's going left.
So you're saying if you're given, sorry, can you say your question again?
Once we find like T1 and T2, and then we have to plug that back into the velocity equation to see which solution is the one going right, which one's the solution going left.
If you're, I guess I'm a little confused on the context where you would have 2 times that you're interested in. Are you thinking about phase still, or?
Just remember, like, there's the for cosine, like there's T1 and then T2.
Oh, I see. Yes. So yes, you're exactly right. Sorry, I misunderstood at first, but so yes, when you're trying to find the time that some position occurs, you want to get your 2 solutions, and then you're correct that you have to plug each of those, but you don't have to plug the 2 pi in part. Just plug in the primary solution from each branch into the velocity equation, and that'll tell you if it's going right or left. Good. Yeah, you had it, but I was just confused. Okay, so very timely and good questions. You'll have more chance to practice in discussion. I've asked the discussion sections to go over some examples that'll be similar to what you'll do on the quiz. Okay. Well, we may again be in a case where the computer doesn't want to do anything. That's not great. There we go. Okay, so moving on to chapter 16, which is on traveling waves. So before we dive into this, what I want to preface it with is when you're looking at traveling waves, there are going to be a lot of similarities between them, the mathematical form of a traveling wave and the mathematical form of an oscillation. And this isn't an accident. We can think about traveling waves in two different ways. So you could imagine if you have a camera, you could take a picture of a wave. And so we call those sorts of plots, or the book calls them snapshot graphs. And a picture, whenever you take one, you have your x-axis is, position, and your y-axis is also a position. Okay, a picture of the real world, if you think of it as a graph, is a position versus position plot. Alternatively, we could look at one little point. So we could have a buoy floating in the ocean, and we could measure how high up is that buoy at each moment in time. And we call that a history plot, or at least the book does. These aren't standard names, but I think they are helpful. And so that would be a position versus time graph. Time would be the independent axis, and it would tell, at a certain time, your buoy would be at a certain position. And it turns out that the motion of that in both cases will be sinusoidal. So both the snapshot and the history plot are both sinusoidal, but in different variables. One will be a function of time, one will be a function of space. And that a traveling wave is really an example of a function that's a function of two different variables. So we need to know, in order to understand a traveling wave, we need to know not only where is the wave, which is a position, but also where does it go as time moves forward, which is time. So there are two inputs to these functions, position and time. And there's one output, which is the height of the wave, the displacement. And so it's hard for humans to look at plots like this because you have to have a 3D plot in order to show a function with two inputs and one output. But we can look at the snapshot graphs and we can look at the history graphs, and we'll dive into these things in more detail and gain a lot of valuable information. But the important thing that connects chapter 16 to chapter 15 is that for the individual masses, like the buoy on the ocean or a little bit of the rope, they actually act exactly like simple harmonic oscillators. So a wave is really just an infinity of simple harmonic oscillators that are all oscillating up and down, but that are connected to each other on their sides. And so as one oscillates up, it pulls its neighbors up with it, and that in turn pulls its neighbors, and that's the process by which a wave travels. Okay, so with that kind of grand narrative in our minds, we can look at the two major types of waves, so transverse waves and longitudinal waves, which you've probably learned about in middle school. For this class, we're going to just mathematically describe all waves as if they were transverse, because really, when we have some compressed region like this, we can just think of that mathematically as a little hump in our wave line. And so they're identically describable. You can use the same formula, the same apparatus to talk about both of them. You just have to recognize that at the end of the day, there are two different ways that waves can move. They can either move by displacing things up and down, which is a transverse wave, or by compressing things in the direction of their travel, which is a longitudinal wave. And in fact, a lot of things actually have ways that they can travel in both of these modes. So if we think about an electron as a wave, which is something that in quantum physics we do a lot of, and you'll see a little bit about in 3C, we actually say that the electron wave has some modes that are transverse and also some modes that are longitudinal. So we have both at once. Photon waves, though, so light waves, are only describable as transverse waves. This is actually a really important fact that you would learn in a quantum field theory class, but that is also relevant for 3C, where you'll do polarization. So there are only two polarization directions for light, because light can only be a transverse wave. But the important thing from this slide is just that they're both identically describable mathematically. And then we also see an example of a water wave here on the right. And you'll notice that when waves are generated, they often actually spread out circularly or spherically. So for example, I'm speaking right now, so I'm making sound waves, and they're spreading out on these big spherical arcs across the room. Of course, they're going to bounce around and do a bunch of funny stuff. But when I start speaking, they're pretty spherical. But by the time they reach you all, we can think about how as you get bigger and bigger spheres, those waves start to look like they're more and more parallel. So we'll see this in more detail later in the slides, but even these spherical or circular waves, we can treat very similarly when we're thinking about the math behind them. And once we're far enough away, we can just think of them as normal sorts of transverse waves. Okay, so we might wonder, what are some properties of waves? And it really depends on both the way we make the wave and what type of medium the wave is traveling through. So we talk about the medium of a wave being the thing that is moving. So for an ocean wave, the medium is water. For a sound wave, the medium is air. And for a wave on a string or on a spring, the medium is that string. And so for a string, we can define something known as a linear mass density. And in general, we think of density as a mass per volume, but you can kind of collapse some of those dimensions if you have a structure that is of a smaller number of dimensions approximately. So for example, a string is basically a one-dimensional object. You can go left or right on a string, but we can, to good approximation, ignore the fact that it has some thickness in the other two directions. And so what we can do when we're talking about the density of a string is we can just take its mass and say how much mass is there per unit length. And this is a really reasonable thing to do for a string because it's basically a one-dimensional object. And so if you go to the rope, or if you go to the store to buy some rope, they'll actually give you measurements like this on the package a lot of the time. So they might tell you how many grams per meter your rope, like how much mass it has in each meter chunk. And that tells you something about the thickness and the composition, right? So it could be more massive because it's thicker or because it has a different composition, one fiber versus another. But anyways, when we're thinking about these wave pulses traveling along our rope, which remember, the shape, that function does travel left to right, but each little mass is just going up and down. This can be hard to visualize, but each little chunk of rope is just a harmonic oscillator, and it pulls up its neighbor, but then because of a restoring force, that little chunk gets pulled back down to the center. And so what happens is this wave travels, or seems to travel down the string, even though none of the individual bits of mass are actually moving. And so for such a wave on a string, if we want to know how fast that pulse travels, it follows a really nice formula, which is written here, where this is the tension, and this is that linear mass density. And so the tighter we pull this rope, the faster the wave pulses are going to travel down it. But the heavier the rope is, so if it's like a steel chain instead of a bit of paracord or something, the heavier it is, the slower the pulses will travel down it. And we just have to plug into this formula. And if you look at the units, we end up getting meters per second out. So it all works fine and dandy. And so we can do a practice problem here. So spiders are very sensitive to vibrations, and a spider will sort of sit in the center of its web, where there are a bunch of strings going out from it. And they'll sort of feel for the vibrations caused by insects. So if a little bug lands on this side, then it'll send a wave pulse that'll travel down the thread to the spider. And in this question, they tell us to assume that these spider silk strands have a linear density of 0.01 grams per meter, and that they're under a tension of 0.15 newtons. And so they tell us that the insect lands at a distance of 30 centimeters away, or 0.3 meters. And we want to find out delta T in this question. Okay, so we can think about these two bits first. We know that velocity is the distance over delta T. So if we can just get the velocity of the wave pulse, then we can quickly get the time, since we already know the distance. And we have a velocity formula, root T over mu. So you can see that these wave pulse travel questions often are very straightforward. They're, really designed to be relatively easy. And so we can plug in, well, first we need to make sure to convert our mu into kilograms per meter. So right now this is 10 to the minus 2. So we need to divide again by 1,000. So we have 10 to the minus 5 kilograms per meter. And now we can just plug those two values in, and I get 120 meters per second, which is quite fast. Remember, the conversion between meters per second and miles per hour is roughly a factor of 2. So these wave pulses are traveling at like 240 miles per hour, roughly. So very fast. And now we can just plug that into our time as distance over velocity formula. And I get roughly 2.5 milliseconds as the answer to this portion. Okay, so it's, like I said, pretty straightforward. You'll occasionally have to use some, basic velocity as distance over time, but waves like this won't accelerate or decelerate. So we don't have to worry about kinematics or anything like that. Any questions about this problem? Yes.
Just make sure T is tension.
T here is tension, yes. Okay, so moving on to section 16.2. So again, we call these little bumps on a string wave pulses. And I just want to distinguish those from the sinusoidal waves that we'll see later, which we'll assume are just infinitely being produced. So these wave pulses is like if you had a string stretched across the room and you just moved your hand up and down once, you would make a little wave pulse and it would seem to travel down the rope as each oscillator pulls on its neighbor. And so just a bit of vocabulary, we call the edge that's traveling at the front of the wave the leading edge, and we call the one traveling at the back the trailing edge. And the rest of this is basically describing what I was relaying to you, but they importantly add that the x position of the peak of this is changing by this amount v delta t, right? This is just the definition of velocity, but we will see this more later. And what I just want to tell you right now is that if we have some function f of x, so I know you're probably all familiar with normal distributions, Gaussians. So let's say we have a Gaussian, and that's our wave pulse. And let's say now that we want to make it move. Okay, mathematically speaking, how do we do that? Well, it's really easy. Instead of f of x, we just say f of x, minus delta x, but our delta x is vt. So we can make any function into a traveling wave by just plopping in everywhere there's an x, plopping in an x minus vt, and that'll cause it to move to the right. Or alternatively, we could plop in an x plus vt, that would cause it to move to the left. So mathematically, it's actually really straightforward. It's just that visualizing and interpreting these things can get rather tricky since they are functions of two variables, x and t. So they just require 3 dimensions to really visualize fully. And so that's what they're trying to show you here. So this plot on the right is an example of a 3-dimensional plot. So you can see that we have a wave pulse. And if you looked at it from the right side, so from over here, this is what you would see happening. You would see it first at this leftmost position, and then you would see it at the next position, the next position, the next position, the next position. So this x-axis is like the physical location of the wave, and then this time axis is telling you how that location distribution is changing with time. And so we talk about this in terms of displacement. So this d of x comma t. So, one example of that was what we just wrote down earlier, that we could have a Gaussian function and we could just replace every x with an x minus vt, and this would get us this 2-dimensional function. In your textbook, they just always want to call this a displacement function, since for a transverse wave, this d of x comma t is telling you how high up or down the wave is at that moment. If it's a positive number, it's telling you that the wave is above the horizontal. It's a negative number, it's below the horizontal. Okay, any questions about this set of plots here? Okay, good. So let's try out a question then. So the graph at the right is the history graph, right? So this is a position versus time plot, this graph on the right. So it's telling you for a single point on the string, where is it located vertically at each moment in time? So it's like if I watched a buoy floating on the ocean as a wave passed by, what is the position vertically of the buoy at every moment in time? That's what this graph is plotting. So it's a history graph for the position x equals 4 meters of a wave traveling to the right at 2 meters per second. Which is the history graph of this wave at x equals 0 meters? Okay, so our wave is traveling to the right. So was it at x equals 0 at an earlier time or a later time? I think I heard a couple people say it. So an earlier time, right? If it's traveling to the right, then it started off, maybe somewhere near 0, and now it's at a position of somewhere closer to 4, at least at time 4. So at time 4, the wave has just barely reached position x equals 4. So what we can do now is they tell us that it moves at 2 meters per second. So we can ask, at what time would it be at position 0? Okay, and it's just a matter of using this delta x equals v delta t function. So if it were 4 meters earlier, so instead of position 4 at position 0, then our delta x would be 4. And if it were traveling at a velocity of 2 meters per second, then this would be 2. And we're just solving for delta t. So we see that this occurred 2 seconds earlier. So instead of beginning at position 4, we know that our pulse hits point 0 at time 2. And we can see that all of the times are shifted over by 2. So instead of getting to that plateau at time 6 seconds, it got to this plateau at time 4 seconds. Every time is shifted over uniformly because the wave is traveling at a constant velocity. Okay. So this option B would be the correct history graph for the position x equals 0 meters, showing how it moves up and down vertically as a function of time. Are there any questions about this one? I think this is where you start to see that these, history graphs and snapshot graphs, they can get a little tricky when you're asked to kind of relate them to each other. Okay. So now section 16.3, this is beginning to get into the main impetus for this chapter. And so all the waves we'll see from now on, for the most part, will be these sinusoidal waves. And the main reason for that is that real world waves, so things like light and sound, are well described by sinusoids. And, if you think about it, it's a natural shape for a wave because waves are created from a bunch of simple harmonic oscillators. And so if you connect a bunch of sines and cosines together, you get more sines and cosines, basically. It's just turtles all the way down. And so again, on the bottom left, we see a full three-dimensional representation of a sinusoid wave. So for example, we have this crest of the wave here, and at a later time, it's shifted over to the right a little bit. And at a later time, it's shifted over farther and farther to the right. So we can see that this wave is traveling rightward. So looking from this side is what you would physically see. And then these time slices tell you where you would physically see that wave positioned at different moments in time. And just like the case of oscillators, we can talk about a period or a frequency of the wave by asking, effectively for these history graphs. So thinking about one point. So for example, this is in perspective, so it's a little hard to do, but thinking about one point in position, let's call it x1, and asking ourselves, how long does it take for the particles at x1 to go from one crest maybe to the next crest? Basically, how long does it take for one oscillator, one position, to oscillate over a full cycle? And that's what we define as the period. And then we can just say the period is 1 over the frequency, just like the case of the oscillator. So remember, waves are built out of oscillators. So all of the tools that we've developed in the last chapter, we can keep applying them here. And especially so given that we're going to be looking at these sinusoidal waves primarily. So you'll see lots of sines and cosines basically for the next while. So they show this here. So on the left, we have a history graph. So remember, that's looking at one particle on this wave. How does it moving up and down? And we define the period as how long it takes for that particle to go from like its maximum position up, and then it goes back down and then comes back to that maximum position up. So that's one period. However, we have something new as well, which is that for the snapshot graph, so if I take a picture of the ocean wave, I could get out my tape measure and I can measure the physical distance from the top of the wave to the next top of the wave. And we call this the wavelength lambda. So this wavelength is basically if we wanted to do something like a period, but on these snapshot graphs. So a period is from the history graph, looking at one oscillator, how it moves up and down. But the wavelength is a property that you would visually see. And if you're at the ocean, I've done this before, you look really dorky, but it's possible. You can take a tape measure and kind of run with a wave and measure its wavelength. And so it's a real, property of the wave that's in physical space related to a snapshot. Okay, so I know there's a lot going on this slide, but all of the pictures are of the same wave, just at different times. So this is a whole bunch of snapshot graphs. So you can see that this one is at time 0, and then we advance the time forward little by little until we've gone through one whole period. I just wanted to give you a chance to have these pictures all together. So the black arrow here is one crest of the wave, and you can see that as time ticks by, that crest moves some amount, and the total amount that it moved is one wavelength. Okay, so it moved one wavelength, and how long did it take to move that far? Well, it took one period worth of time, because in order for this point on the left to have gone from a peak to a peak again, that takes one period. And over that time, since this wave is regularly spaced periodic, the crest will have moved one wavelength. So putting this together, we can talk about, and this is a fundamental relationship, the speed of a wave, of a periodic wave, is the wavelength times the frequency. And we can see that the units work out. So the wavelength is meters per cycle, and the frequency is cycles per second. So when we put this together, we get a velocity, which is meters per second. So if you forget how you were supposed to order this equation, I mean, it'll be on your formula sheets realistically, but if you're just, in your daily life or trying to do the homework or something, just think about the units. Frequency is 1 over time, wavelength is distance, and so we just have to multiply the two and we'll get a velocity. And I really like what the book mentions here, so I wanted to include that too, which is that the speed of the wave is a property of the medium. So for example, we'll see this in a moment, that sound waves have different speeds depending on what substance they're traveling through. So sound actually travels faster underwater than it does in the air. And it's just a property for sound waves, you're just thinking about how quickly those molecules can bounce into each other. So it's telling you about the density of the material, basically, the density and the stiffness of the material. And so the speed of a wave, purely a property of the material, whereas the frequency of a wave is a property of how you made the wave. So if I have a string and I just wiggle my hand up and down really, really fast, that's going to be a high frequency wave. Or when I'm speaking, if I just vibrate my vocal cords really fast, that'll make the pitch of my voice higher. Unfortunately, I can't change the pitch of my personal voice very much, but if someone more talented, you can imagine them doing such. So putting them together, we see that the wavelength is really a composite property. So like I said, we'll continue to see examples of this, but the frequency is something that doesn't change as a wave travels. But if a wave goes from one material to the other, the velocity very well might change. So that would cause the wavelength to be different. Okay, so the wavelength, since it's a composite property, both from the medium that the wave's traveling through and the source of the wave combined together, the wavelength is a changeable thing. So if a wave moves from one substance to another, then we'll see that wavelength change. Okay, so for an example, what is the frequency of this traveling wave? So how do we make some progress here? Okay, so they tell us the velocity. That one's a little obvious, right? It's 50 meters per second. We want to know the frequency, and presumably we're going to use our new equation, that V is lambda F. How do we get the wavelength? So we have to just kind of estimate it from the plot. So you can see that at this position, so this is a snapshot graph. So at this green dot, we're at X position 0. And if we look where we next get this same displacement, it's roughly at 10. I mean, it's not exact, but we could say the wavelength is roughly 10 meters. And so now we can just divide those two, and we get a frequency of around 5 hertz. Okay, so in a problem like this, you might say, okay, Cannon, I can't really accurately estimate this wavelength, and I'll say, fair enough, me neither. But if you look at the possible answers, there's only one that's even close, so just pick that one. So if you're having trouble estimating off of a plot, it shouldn't matter in any problem that you're given. And if it seems like it's giving you the wrong answer, like in the homework, just talk to me, because it's probably just a poorly made question. In reality, I just want to spend a moment to tell you about this. There's a really great tool called Web Plot Digitizer that lets you take pictures of plots and click on a pixel specific location on the axes, and then you can trace out the data points and get them in a comma separated variable list or something like that. So it's really, really handy if you ever want to do a research project or just get very, very accurate readings from these graphs, you can use WebPlot Digitizer. So if you're really interested, that's what you should do. Anyways, so then how do we represent these sinusoidal waves? Well, just like I said earlier, we can take any function f of x, and we can instead write it as f of x plus or minus vt, and we get a traveling wave. In the case of sinusoids, we typically write it slightly differently, just to have the convenience of the wavelength being nicely separated from the frequency. And so you'll see in this upper left, this is a wave at time 0. So this is just a snapshot graph, right? And what we have is the position x. So that's the independent variable here. We have to divide it by some scaling factor. So we divide it by lambda, because lambda is how many meters are there per cycle. So now x over lambda, that's telling you what fraction of a cycle you're at. So if x over lambda is 1/2, then I've gone through half a cycle of my wave. And then by multiplying that by 2 pi, which is the number of radians per cycle, I've converted that fraction into an angle. So that's why we have 2 pi x over lambda, is that we're converting a position into a relative location on the wave based on the wavelength, and then turning that into an angle. And the phi naught here is just representing that that wave might not be a pure sine, it could be shifted one way or the other. And so then to make this traveling wave, we just have to plop in an x minus vt instead of an x. That's all we do for any function. So this would be a wave traveling to the right. And then yet again, to make our lives easier, we don't want to write 2 pi every 5 seconds. So we create these new variables. So we've already seen omega. This is the angular frequency that we saw for oscillators. And then our new thing is this k, which is called the wave number. Okay, so the wave number, it's a weird thing. It's inversely related to the wavelength. So a bigger wavelength will correspond to a smaller wave number, but it's containing that same information. So it's just a way of speaking about how physically long a wave is. But instead of doing so in terms of an actual distance, it's looking at the inverse of that. And there's no really good reason to do so other than that you don't have to write something as a fraction. So there's really laziness all the way down here. But what you can see is that we have a 2 pi over lambda times x. So this thing is just our k. And then we have a 2 pi v over lambda. And remember, v over lambda is just f. So this thing is just our omega. So what defining omega and k lets us do is write a much more beautiful formula without any pesky 2 pi's. So this d of x comma t is the formula that you should be using all the time for your sinusoidal waves when you're trying to do homework problems or quiz problems, anything like that. And so this k is telling you something about how physically big these waves are, right? This is 2 pi over lambda. And this omega is telling you something about how fast it's oscillating back and forth, up and down. And so together, they tell you how this wave not only looks at each moment in time, but how it's spread out spatially. And these sinusoidal waves are mathematically infinitely long. So of course, that's not physical. If we plot a sinusoidal wave, if you type into your calculator, a sine kx minus omega t, it's just going to plot something that goes to the left and the right forever at each moment in time. But in reality, we're going to only consider some certain physical range as being actually describing are described by this function. So just be aware of that. You'll find an infinite number of solutions. For example, if you want to know at what time does some displacement occur, but only typically the positive ones will be describing your real physical system. So just like the case of the oscillator. So we have a long involved example here, but it's about halfway. So let's take our 5-minute break, and you can stare at this if you'd like, but I'd encourage you not to.
I don't understand. There's the videos like this, and then all the different drawings. I draw this. Oh. What is your research partner for your PhD?
I do a bunch of stuff, but it's basically like dark matter cosmology type of things. So I work on like sterile neutrinos and different dark matter particle models.
Oh, okay. So quantums?
Yeah, I mean, it's definitely a part of it. It's not like classical quantum mechanics. It's like, we have to use some bits of quantum field theory to look at how the particles behave, but it's also combining that with like cosmology stuff, so general relativity and Boltzmann equations, not the ones we've seen in class. There's just so much stuff named over Boltzmann.
So you do it wave stuff, right?
Did I say again?
You do it wave, right?
Yeah, certainly. So waves are a big part of quantum field theory, because you learn that everything is a wave function, which is just a wave and probability space, basically. It's a little weird, but
It's cool. So because I searched you up online, and then you worked in the labs with that much dark matter stuff and cosmology. So I wonder, so like what they trying to do with dark matter stuff? I thought about like science fiction and stuff like that.
So yeah, it gets a lot of weird science fiction coverage, but it's really not too crazy. It's just that we look out at the universe and we notice that there's more gravitational effects than there is matter. So there has to be something causing that. And so you could take as one hypothetical that there's some extra matter that we just
Oh.
can't see. We call it dark matter.
Wait, so are you dealing with like theoretical stuff or?
Yeah, I do, well, I did experimental in undergrad a little bit,
I
but
see,
in
I
grad
see.
school I do only do it.
Oh, okay.
Yeah, mostly just
Okay.
pen and paper and like computer simulations.
Oh, I see.
Yeah.
So is it like hard because you cannot check your error and stuff, right?
There are also ways to check, so we do have actual astronomical evidence.
Oh, okay, okay.
So you can, and an important part of what we do is actually compare things that we think about to those bits of evidence. So I don't know how much you've heard about these things, but there's like the cosmic microwave radiation. So we can measure intricate details of that and compare it to what we predict. And then there are distribution of galaxies, we can kind of predict those things too. Anyways, we should get started back with the thing, but thanks for asking. We can talk more after.
Yeah, totally.
Okay, so let's go ahead and dive into this long example problem, but I think it's important to give you all some practice with these traveling waves. So we have a sinusoidal wave with an amplitude of 1 centimeter. So we can go ahead and write that down. A frequency of 100 hertz. And a speed of 200 meters per second in the positive x direction. And at t0, it's at a the 0.1 meter is on the crest of the wave. So at t equals 0, we can draw our snapshot plot, and we know that this 0.1 is on the crest. So we have something like this happening. Okay, so the first part is they just want us to calculate everything that they could potentially that you could potentially be curious about. So there are a few steps that are pretty easy. So we know that lambda is just v over f. So that's very straightforward. 200 over 100, it's just 2 meters. K, they want us to calculate. So this is just 2 pi over lambda. You can see a lot of this is just plugging into formulas. So that's just pi radians per meter. And then omega is just 2 pi f. So this is 200 times pi radians per second, but we could just multiply that out. So 628-ish radians per second. And the period is 1 over the frequency. So that's 0.1 seconds. Did I mess that up? Yes, I think I did. Yeah, 0.01. Yes, okay. So then the last thing for part A is getting the phase, which as you'd expect is always kind of tricky. And so what we want to do here is we want to think about how is this function shifted to allow for this position at time 0 to have a crest at point at 1. And so we have to think here, are we going to use a sine or a cosine? So for the sinusoidal traveling waves, the book tends to use sine. So fair enough, we can certainly do that. And in the case where this was a sine wave, we would have something that looks like this, where our first crest would be at a position, so this is again x versus t, would be at a position in sort of angle space of pi over 2, and we need to convert that into position, and that's where the wave number comes into effect. So k times x needs to be pi over 2 for the case of just a pure sine wave. And k is this wave number that we already found is just pi. So for a pure sine wave, the first crest would be at 1/2 meters using this formula. And so we need to shift everything over by some amount. And so in order to figure that out, what we can do is we can just say that kx plus phi needs to be pi over 2. So we know that the crest happens in angle space at pi over 2. And instead of just having this kx, we add an extra phi to our equation here, this phi naught. And that's what's going to allow the x to be a different size than just 1/2. And so plugging in x equals 1 and our k equals pi, this is just pi. So we have pi plus phi equals pi over 2. And so we get a phi of negative pi over 2. Let's write it up here. So that's the hard one from part A. So depending on if they tell you information about the snapshot graph or the history graph, you'll have to use either kx or the omega t portion to find the phase. You can see how the phase is in here in the argument. It's added to the kx and to the omega t parts, so it affects them both. And so if they tell you something like this problem, where they say that at time 0, a 0.1 meters has a maximum displacement, that's telling you something about a snapshot graph. You're going to want to use this kx plus phi equals, and then for a crest, that'll be pi over 2. For, a trough, the first trough, that would be 3 pi over 2. So thinking about where a sine wave has these critical values. But they might just as well tell you something about the time. So they might say position x equals 0 at time 2 seconds has a crest. And in that case, you would have to say minus omega t plus phi naught is pi over 2. So it's a little tricky. You'll have some chance to practice this in discussion and in the homework, but hopefully this example is also beneficial. So anyways, now that we have all the pieces, we can easily write our wave equation. So our d of x comma t for part B, we just write it as, plugging into this formula. So our a is 0.01. Then we have sine. Our k is just pi x. And our omega is 628 t. And then we have minus pi over 2. So this is our answer to part B. So once you get all the pieces, you just put them into the equation. And as long as it's a sinusoidal wave, it'll be a valid solution. And then finally, they want us to draw a snapshot of the function at time t equals 0. So that would be, this is the x position, this is the displacement. And so these sorts of questions can get really tedious really quickly. So I'm not going to tend to ask you to do them personally, but I think there might be one of them in the homework. Again, you won't have to draw it there. You'll just have to pick like the right option, basically. But they already tell us at time 0 that a position of 1 has a crest. And we know that the wavelength is 2 meters. So we know that if we go over to position 3, that we'll have another crest. So we have a trough down here, we have a trough down here, we have a crest up here. So this tells you pretty well what the wave looks like. It looks, if I can draw it accurately. Looks something like that. And then the details, don't worry too much about. You should just be able to basically find the location of one point. Usually it's convenient if you find the location of a crest or a trough, and then just draw the other ones based on the wavelength, if you're drawing a snapshot plot. So right, this distance here is the wavelength, which is in this case just 2 meters. Yes.
Kind of going back to the history graphs you were showing earlier. Is the displacement and the delta with I this thing.
Yeah, they are. So all of the pictures I'm using are just from the book because I was like, the book will be consistent. No, it won't. But at least in the section 16.3 and beyond, they are pretty consistent about using D as the variable to tell you sort of how high up or down is each particle, right? And for a lot of these, if you imagine ocean waves, it's really helpful, I think. So the 0 for ocean waves is just sea level. And then this D variable is telling you how high above that or below that each little point on the wave is. And then, if you take a picture or just look at the wave, then the horizontal axis is space. So it would be like the snapshot. And then if you watch those waves move, they're moving through time as well. So that's why we have to think also about that second variable. So very good question. Any other questions about this example? Okay, so this is, getting the part B would be a typical type of question that I think is very reasonable for you to be able to answer. Yes.
Could you remember how you got the phase again?
Yeah, so in this case, the information that tells you the phase is this bit, this whole thing actually. So they tell you a set of initial conditions, basically. They say at time 0, at position 1 meter, you're on a crest. So you have a plus A as your displacement. This is telling you that D at t equals 0, x equals 1, this equals positive A. That's how you would write that sentence mathematically. And so on the crest of a wave, if you're thinking about a sine function, this crest happens at an angle of pi over 2. And you can think that the k, this wave number, what it does is it converts distances to angles. So we know that the time is 0. So, we had this kx minus omega t plus phi. Our time is 0, so we don't have to think about this omega t part. We just have to say to ourselves, at what moment in space, or sorry, at what, well, we're trying to solve for phi here. So for what phi do we have some input to our sine function that matches our expectations of a crest? And so we know that a sine function has a crest when the argument is pi over 2. And so that's how we get this relationship here, that kx plus phi is pi over 2. And then we just have to plug in x equals 1. And then our k we found earlier is just pi. So this is saying that at position 1, at time 0, so that's how we canceled out that omega t, we can, we're told that we're at a crest, so we expect the argument to be pi over 2, because sine of pi over 2 is going to output 1. And so how do we make that happen? Well, we have to adjust phi. That's the thing we don't know. And so we can then solve this equation for phi, since there's only one variable, and get, in this case, negative pi over 2. So good. I'm glad you asked that, because I should have slowed down a little bit earlier. But you can see how if I told you at time, so if I told you exactly the same thing, but instead of time 0, I said time 2, you would just have to plug in 2 into this minus omega t bit. So your initial condition doesn't have to be at time 0 or at position 0. It could be some wacky combination. I could tell you at position -2, at time, positive 50, we have a crest. And then you could set that equal to pi over 2.
And just one more thing, how can you have a x equals 1/2 meters down there, the lower left corner?
Oh, sorry. So this was an example. So this isn't for this problem, but this is saying if we did have a pure sine function, what x position would the first crest be in if we had the same wave number pi? And so in that case, so basically that's the same thing as saying for this exact problem, if we didn't know the initial conditions and we just said the phase is 0, what would it look like? And it would look like this plot, where this crest pi over 2 occurs at 1/2 a meter. So you can see how that negative phase has shifted this function to the right. So by having a phase of negative pi over 2, we've shifted the whole thing to the right, such that instead of having the first crest at 1/2 a meter, it's now at 1 meter. Moved it to the right by subtracting something from the argument. Very good. Okay, so rewatch this section if it's confusing, or talk to your discussion leader or me in office hours. But we'll move on a little bit. So like I've said a few times, we can think of each particle on a wave as a simple harmonic oscillator. And so we can ask ourselves, and this is a subtle detail that people often mess up, including me sometimes. There's the velocity of the wave pulse, which is lambda times f, or, you know, on a string, it's root t over mu. But there's also the velocity, the up and down, the vertical velocity of each particle. And so if we take the derivative of the displacement and we get something very similar to what we got for simple harmonic motion, this negative omega a cosine blah, 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 that's telling you the vertical velocity of each particle at each moment in time. Okay, so if I plug in some specific position, then now I have a function of time that'll tell me for that position, what is the velocity at each moment in the up and down direction. Okay, and so you can see that the maximum velocity, again, is just going to be omega a. So it's the same equation as we had for the oscillator, and that's because each little mass on the string is an oscillator just in the vertical direction. Okay, so when it passes through the origin, that horizontal line, it'll have its energy entirely in the form of kinetic energy, and it'll be moving at its fastest speed, which is just omega a. And it could be positive omega a, meaning it's moving upward, or negative omega a, meaning it's moving downward. Okay, so I think that there is at least one homework question where they ask you to do this, but it's something that's really critical, that if you take the time derivative of displacement, you don't get the speed of the wave. This is a super common mistake. You get the speed of the individual particles in the direction of the displacement, so up and down for a transverse wave. Okay. Okay, so now moving on from sinusoidal waves, I mean, these are still sinusoidal waves, but moving into the next labeled section, so sound and light. This is where we actually see why we care about these things, basically, because our two primary senses are definitely hearing and vision. And so those are both carried by some sort of sinusoidal wave. So vision is a transverse wave, whereas sound is a longitudinal wave. But like I said, mathematically, they're identical. And so we can see that for sound, the way that the wave propagates is that these particles are, some pressure is applied at some frequency. So for example, when I'm speaking, I'm applying a pressure to the air with my vocal cords at some frequency, and that causes an alternating compression and refraction to the air. So in some regions, they'll have a little bit more than atmospheric pressure. In some regions, they'll have a little bit less. And this pushing is going to push in on its neighbors. That's going to cause this wave to appear to move forward. And, you know, if we change the frequency or change the amplitude, we can actually use this to convey information. So even though those individual particles are not traveling from me to you, so the air particles near my mouth, you know, which is good for sanitary reasons, I guess, are staying near my mouth, and the ones hitting your ear are different, but they're able to transmit information because they're bouncing into each other, and I'm varying some fundamental property of the wave, notably the frequency and the amplitude. Okay, so there's a lot of stuff here, but we learned that the RMS velocity of a gas molecule is √3 kBt over the mass of that particle. And so it turns out that there's a nice derivation that I'm not going to do for you, where if you say to yourself, okay, I have a sound wave, I know that heat probably isn't very important to a sound wave. So a sound wave is an example of an adiabatic process. So if I use all of the thermo stuff we learned, and then go a bit beyond it, you can derive with the ideal gas law and some assumptions about heat being zero, or heat change being zero, that the speed of sound in a gas follows this relationship. So we still have the kBt and the m. This gamma is the ratio of the heat capacity at constant pressure to the heat capacity at constant volume. And remember now that the heat capacity at constant volume for a gas is d over 2 times r. And at constant pressure, it's d over 2 times r plus 1 r. So we could just write this as d plus 2 over 2 times r. And so you can see that what you end up getting is d plus 2 over d, where this d was the degrees of freedom of the structure. So for a monatomic gas, that d is just 3, because you have little balls that can move and left and right, up and down, or forward and back. For a diatomic gas, that d is 5. So you can see immediately from this formula that we expect a diatomic gas to have a different speed of sound than a monatomic gas, even if the particles have the same mass and they're at the same temperature. So that's a nice bit of physics. Now this capital M is a molar mass. So this is like a kilograms per mole. So in general, I would recommend just using this formula if you're being asked to think about the speed of sound from a thermodynamic standpoint, because the kilogram per mole molar mass is often something that causes some problems for people. And it's usually easier to just say how many, protons and neutrons are in a nucleus, multiply that by the proton mass and plug it in for M. So we give you some example speeds of sound in different materials. So this formula on the left is only for the speed of sound in a gas, but you can see that in general, the denser the material, the higher the speed of sound. And especially for metals, they have an extraordinarily high speed of sound. And if we want to understand why that is, we have to look at a slightly different formula, which is that the velocity is the square root of the stiffness over the density. So this thing, for a fluid, we call it the bulk modulus. I know these are scary names, but for a solid, we call it the Young's modulus. But at the end of the day, whatever's in the numerator is just telling you something about how stiff those atomic bonds are. And remember, we had the formula earlier for a string that the velocity of a wave is the tension over the linear density. And so you can see it's a really, really similar idea. We're going to take the square root of something telling us how much force is involved, how stiff it is, and divide it by something telling us how much mass there is in the system. So how much mass per length there is for a string, or how much mass per volume there is for a solid or a gas or a liquid. And so I give you some example bulk moduli for different materials, or some of these are also Young's modulus as well for the solids. And you can see that in general, for these more metallic materials or something like diamond that has a very strong regular crystal structure, you get a very high stiffness. So diamonds are very stiff relative to compressive forces. Whereas for something like sandstone, if you've ever played with it, you can just kind of press on it really hard and break it into pieces. It's like a compacted form of sand. It has a much smaller bulk modulus. And so for those things like sandstone, we expect the speed of sound to be lower because there aren't as many opportunities for these molecules to transmit forces, which is what causes the wave to move. And so both of these velocities formulas, this v sound on this slide and these two velocities here, these are all telling you the speed of the wave pulse traveling, right? That's in contrast to the earlier formula, the derivative of displacement, which is telling you the speed of the things moving up and down, the individual oscillators. Okay, and so if you plug into that first formula, then the gamma for air is about 1.4. It's mostly made of diatomic oxygen and diatomic nitrogen. The ideal gas constant we have there. We can take a room temperature, 293 Kelvin, and if we find the molar mass in kilograms per mole of on average of air, so a weighted average based on how much nitrogen, how much oxygen, then we get about 0.029 kilograms per mole. And so we get the standard, this is the thing that you're going to want to use in your homework and everything, speed of sound in air of 343 meters per second. Now there's a really nice empirical formula that's not in your book, but that I do expect you to be able to use. And so it'll be like on your formula sheets if you need it, which is that if we know the temperature in Celsius, we can just multiply that by 0.6 and add it to 331. And for any normal temperature, like anything you would experience on Earth, this works quite well for gas in our atmosphere. But remember, you know, if you have a different type of gas, if we had a monatomic gas instead, then we would have a different speed of sound. Or if we were at a different temperature, or if it has a different composition. So if the air is more humid, then the speed of sound changes. So the speed of sound is very fickle, but it tends to be, you know, 300 and something meters per second, which is roughly 600-700 miles per hour. And so I give the example of lightning here just because there's a common trick that many of you may have heard of, where you can see a lightning flash. Light travels much, much faster than this. And then at some amount of time later, you'll hear it as thunder. And so by comparing those two, you can roughly tell how far away that particular lightning flash occurred at. But you should be careful using this to predict things about storms, because a storm can be quite large. So you might think a storm is traveling away from you, but really you just first heard a pulse on one side of it, and then next the flash was on the other side, which tends to happen because of how the charge is distributed for lightning. So don't read too much into these, but it does give you a way of roughly telling how far away a storm is by comparing these travel times. So we'll pick this back up next week. Best of luck with your quiz today. Don't forget to take it after discussion. And I'll see you all on Monday.